this slide is about the schematic of the typical single junction silicon source cell. Okay, we just use this one as an example to show how the structure of the silicon-based source cell, which is considered as a silicon pin junction with a very thin N-pass layer and heavy doped P region. Heavy doped N region at the top and the P region at the bottom. So this kind of structure will be heavy doped N region with a thickness is about 200 nanometers, and that's the diffusion region. And the bottom is about 200 micrometer thick P region. So because you have to use the light shed on the surface. So at the bottom, you cannot make a contact cover the whole surface. So this kind of contact is called some kind of finger electrode, or the other one is called the fishbowl electrode. So you have the finger electrode and this the box electrode for the connection of the whole contact area. And at the bottom, you don't have any issue about the light information. So you should put the bottom contact to cover the whole substrate.
Is the diagram right, wrong?
So this diagram to the right is our observation. So thickness for the N region is about 200 nanometers. At the bottom is about 200 micrometers. So the ratio should be 1 to 1,000. So in the real structures, this one should be very thick. Okay? The N region is very thick. Okay? So the generation of the whole pairs in the pin charge that we should take a look at this absorption coefficient first. So this one is the absorption coefficient for silicon correspond to the visible range. So we have to take this curve into 3 parts. Okay. So I draw a line to cover the N-pass region. Okay. So first one is that since the since the emissions for the light can be divided into 3 parts. One is the short wavelength photons. For those ones are in the range from 300 nanometers to 450 nanometers. Okay, those are the so-called short wavelength photons. Those photons are with to the silicon N-pass region. The absorption coefficient to this short wavelength photon is very high. Okay, high up to as high as 10 to the power of 5 to 6, which corresponds to 200 nanometers to 10 nanometers. So for those kind of short wavelength photons, once the photon was shedding on this surface, getting to the silicon, it will be absorbed just in the N-pass region and to generate the H hole pairs only in the N-pass region. Okay? And for the so-called medium wavelength photons, once they get into the silicon, usually they will be absorbed in the diffusion width region. Once the actual hole pair was generated in the diffusion region, they will be departed by the building potentials, and for the electrons, it will move to the N-pass region and forcibly spill to the P region, and then contribute to the circuitry as the current. Okay. And for the long wave photons, they will be absorbed in the N region, in the P region. However, only those electrons which are the magnetic carriers within the so-called effective distance, diffusion distance, can be helped or have the chance to get into the diffusion region and then drift to the N-pass region to contribute current. So the effective region for the silicon source cell is actually within the range made by the whole diffusion length in the N region and the diffusion width and the actual diffusion length in the P region. Okay, so that is actually the effective area for the silicon source cells to absorb the incident photons to generate the hole pairs. Okay, so look at this figure. Okay, so all those short wave photons will be absorbed within the N-pass region. Okay, and for the photons in the range from 450 nanometers to 900 nanometers, those photons will be absorbed in the diffuse region. Okay, because in this range, for example, for absorption coefficient 10 to the power 4, the unit is 1 of 7 meters. The corresponding absorption depth is about 1 micrometers. So this one usually corresponds to 200 nanometers. Okay, so only within this range, okay, the East photons can be absorbed within this range. Okay, but for the so-called the longer photons like 900 meters to 1.1 micrometers. Okay, the absorption coefficient is more than 200 nanometers. 200 micrometers, sorry, 200 micrometers. That would be out of range for a thickness of a silicon source cell. So all those photons will have no contribution to the upper current. Okay, so here, as we mentioned, that the photogenerated electron hole pairs within the whole effective length, diffusion length, and the diffusion region, and the electron diffusion length can contribute to the photovoltaic effect only within this range, effective. And then usually the electron diffusion length is larger than whole diffusion length. Okay, that means that the effective thickness for the silicon source cell with the device structure N plus P will be able to generate more electron hole pairs than the counterpart counterpart device structures P plus N, this kind of structures. Okay, that's why we always make the silicon source cells as N plus P, this kind of structure. Okay, so the photogenerated electron drift to the N region, and the photogenerated hole drift to the P regions, so that that's the electrons and holes. It could be as the transmitted currents and the photovoltaic voltages. So if this one is open, then you have an open circuit voltage that still is VOC, and if you connect the two sides, there's a current flowing these directions, and this direction is the other directions, the negative directions to the definite direction of the P junction. So that's the flow current. Okay, usually we have a minus sign to label its directions. Okay, so the cell structure design is that the mentioned before that the band gap silicon is about 1.1 volts. So the spatial absorption wavelength is about 1 micrometers, and for the Eastern photon with the wavelength about 1 to 1.2, absorption coefficient is very slow, so the corresponding absorption depth is very large. You're going to need a very thick P regions, but usually this corresponding thickness is about 200 to 500 micrometers. But we're not going to make this source cell that thick, because with a very thick P regions, you're going to increase the series resistance. They'll detrimental to the output performance. So usually thickness about 200 micrometers. So for the Eastern photons within this range, there's no contribution to the output power. And to have most light soaked in the deep regions, the N region must be very thin, about 200 nanometers. But we have to lower the series resistance, so we can dope this N plus region as much as possible. Usually up to the doping level like 10 to the power of 21, 10 to 2 even, so to make the series resistance as low as possible. And since we're gonna make this heavy doped, so the whole diffusion net doesn't have to longer than the origin, because no matter what the N plus region is only 20 nanometers, it's not that thick. So the origin can be doped with a high to reduce the series resistance and provide a very good metal contact to lower the current resistance. Okay, so next one is the source cell characteristics.